Hi everyone. So today we'll be solving the problem on GeeksForGeeks problem of the day, LRU cache. Now this question is marked as hard, but it's not really hard. It's a tricky question, but I think it's a medium at best. If you really know the trick of the question, and I would say yeah, it's a tricky question, but it's not really hard. So let's first read the question and understand. Design a data structure that works like a LRU cache. Here cap denotes capacity and Q denotes number of queries. So it's a fixed sized data structure. You can have a put key value which puts the key and value into the cache. And you have a get which retrieves the value from the cache. If it doesn't exist, return -1. And it has get and put method and the constructor which we are given here. I'll be solving this in C++, but I'll attach the Java and Python solutions as well. So let's move forward. Yeah. So I have this. What is an LRU cache? Let's first understand it. And this picture is a very good way of understanding an LRU cache. And I got this from covio.com. So this is not something I created. But yeah, so an LRU cache basically you have a data structure which stores the data, and you have a lookup data structure which helps you retrieve the data. Now we will look at it and understand it deeply in a moment. So yeah, this picture is a very good representation of how we are going to design an LRU cache. Now for an LRU cache, it's a very basic concept in computer science, and it's a very deep concept as well. So I'm not going too deeply into the topic. I will only be covering what is important for implementing this question in Leetcode styled problems. So yeah, I'm not going into the LRU theory and the cache eviction algorithms and other things. We'll just touch upon what we need to understand about LRU to implement a Leetcode style problem. Also, there are other types of caches. There is least recently used, there is most recently used, there is least frequently, most frequently, random. Many types of caches are there. Yeah, that's something you can look upon in your free time. So as you can see, this is a very common problem. Uh, you have it in GeeksForGeeks Leetcode interview bit. It gets asked a lot in interviews and Leetcode style questions. So yeah, it's also a very important thing to understand in computer science as well as Leetcode design and all those things. So we'll start today is what is an LRU cache, how does an LRU cache work, and how can we design and implement our own LRU cache. And if you're only looking for the code, I'll attach a timestamp and you can skip to it. But yeah, I'll explain what an LRU cache is to those who don't know. So yeah, for now let's just understand what an LRU cache is. So LRU stands for least recently used, and as the name suggests, it's a cache. So we kind of the main thing about a cache is it needs to be fast. You ideally would not want a slow cache. So whatever operations we are implementing in our LRU, they need to be fast, right? And where does the name LRU, or why does it have the name least recently used? That's because it evicts the least recently used item. What that means is, so since this is a fixed size data structure, when it is approaching its size, uh, it will delete certain items. And which would that certain item be? That would be the least recently used item. So the eviction policy is LRU, and that is where the name comes from. If you don't understand it, that's fine, we will have a look at it later. So yeah, it's a data structure that works on the last used pattern. What that basically means is it is kind of a sorted data structures, and it sorts or orders the nodes inside the data structure based on the last access time. Now when we say last access time, you don't really require to store a timestamp related to every node. Think you could, but how we are doing it, you don't really need to store the timestamps or the access time or something like that. How we'll do that is something we'll have a look at. And since it's a cache it should be fast. The expected time complexity of any operation, whether it is insertion, deletion, lookup, update, anything should be O of 1 ideally. I mean, you could implement a slower O of n cache, but I think that will get you time limit exceeded. Yeah. Space is not an issue. I mean, since you are designing a cache, it is okay to use multiple data structures. What we really care about is the speed. Now LRU, if you are using it at a hardware level, let's say the CPU cache, or even in your RAM, because these are very limited size data storage mechanisms, ideally you would be a bit worried about storage, but in Leetcode style questions you can throw storage out the window and focus on the time complexity. So again, it needs lots of insertions and deletions. Why does it need lots of insertions and deletions? Because it's a fixed size data structure, so it cannot keep growing infinitely. If it cannot keep growing infinitely and you keep adding stuff into it, old stuff needs to be deleted. Only then you can add new stuff. It's a fixed size data structure. Otherwise, if it was infinitely sizable, then you really wouldn't worry about deleting anything, and at that point it wouldn't be a LRU cache, it would just be a cache. Just throw all the data in there, right? And it maintains the insertion order. How we'll maintain an insertion order is something we'll look at next. Yeah. So this is kind of how LRU looks. Again, this picture I showed at the beginning, this is a better representation of how an LRU should look like, but for understanding purposes what I'm showing here works as well. So again, it's a key value pair data structure. What that really means is you are given a key and a value, and from the key you want to retrieve the value. So as you can see, all the values here are separated by a colon. So before the colon you have key, after the colon you have the value. So 8 colon 17 15 colon 91 blah blah blah. Now the important thing to note here is it is kind of maintained in a way where the most recently used item, or the item which was used recently, we performed any operation on that item, whether it was insertion, updation, access, any kind of operation we performed on an element, that should always be at the head, kind of, you can say. And the item which was least recently used, or we used it a long time ago, that should kind of be at the last. So what it really means here is the key minus 128 was used very recently, the key 42 was used before that, the key 1 was used even before that, and key 15 was used even before that, and the key 8 was used some time long back ago. So this is kind of, you can say, stale data. It's been sitting there for a long time, and whichever data was accessed earlier kind of comes to the head, you can say, and the one which is not been used for a while is at the tail, and the name least recently used comes from, because we will kind of delete this 8 if needed. Now when we will delete, how we will delete is we'll look at. Yeah, so this is how you can say LRU looks. You can think of it as a hash map, in a like kind of stack kind of way, with key to the left, value to the right. You can think of it as an array, linked list, anything. Yeah, but this is just to help you understand. So first thing we will look at is the get operation or the access operation. So now we want to have a O of 1 time. How we will implement that is something we'll come to later, but yeah. So let's say we are trying to access the key 1. So it is at the middle of our LRU, and the value is 0. So let's say we are accessing 1, we are getting the value 0 and we are returning it. Now what you want to do when you access it is, whenever it was accessed, whenever a node or an element is accessed, it no longer stays in the middle of or at the end. You need to change its position. So where does it go? It goes to the head, it goes to the starting. As you can see, after the access, before access is at the top half, after access is at the bottom half. So you can say the original position of 1, which is marked by this huge cross, we kind of deleted the old node and inserted a new node at the beginning. So you can think of it as deleting the old node and inserting a new node at the head, Or you can also understand that we just kind of moved it. We moved it from the middle to the beginning. And which was the previous beginning, or which was the previous head, it was minus 128, it moved back. 42 also moved back. So everything kind of moves back one position, and whichever the item we access the latest, that comes to the front or the head. So that's how your access would look like. Okay. uh, then you have insert. Now insert has a few edge cases, but let's consider the most basic example, that the LRU is not at its capacity, which means there is some space left to insert new nodes, and the item does not already exist in the LRU. Okay, that means if you try to find a value by the key 3, it would return -1. Now we're inserting the key value 3 colon 100, key is 3, value is 100. So before insertion is at the top half and after insertion is at the bottom half. So when we are inserting, see the previous head was -128, we'll kind of move it back. So you can see everything just moves one position back, and the latest inserted values, it comes at the head or the front. So this is what a insert operation, when it is not at full capacity and item does not exist, will look like. So this is the easy case. You don't have to worry too much. Just take the new key value, insert it at the head. Very easy, right? Because we are not approaching the capacity yet. The second thing is when you are trying to update a value, this is a bit tricky, or I won't say really tricky, but this is a part where people really need to understand, is when you are updating a value. So the top half is before the update and the bottom half is after the update. So earlier the key 42 had value 33. Now we kind of overwrite or update it. The key 42 then stays the same and the value is 100. Now what you would notice is earlier the key 42 was at the middle of the LRU, not exactly middle, but it was not at the beginning or the end, kind of somewhere in the middle. We moved it to the front or the head, and everything else just kind of moved back one place, right? So this is also what you need to understand it update. Now you can kind of see it as a delete, that the old 4233 was deleted and the new 4200 was inserted at the head, or you can kind of say that you just picked it up and moved it to the front. Anything works, but what you want to achieve is the functionality. The implementation is abstracted and up to you. So yeah, that were kind of the easy things. Now we are doing an insert operation which is not in the data structure. That means it is not in the LRU and it is already at capacity. What that means is, if we try to insert a new object or new node as it is in our LRU, it will kind of overflow its capacity. So that is not something that we want. So let's say the capacity of the LRU is 5, and as you can see at the top half, we already have 5 nodes. So what you need to do now is you need to delete the old node. And which node we will delete? As the name suggests, LRU, least recently used. So 8:17, as you can see this huge X mark on top of it. What that basically means is you need to get rid of this node, delete it, right? And the new least recently used node will become the one before it. So earlier it was 8:17, we deleted 8:17, and now the tail or least recently used becomes 15:91. So this is how you kind of do it. And when you inserted 5:20, that key value pair node comes at the front, and this is the most recently used. Now you can do any number of operations you want. If you also want, you can kind of free the memory for this LRU node to prevent memory leaks, but yeah, for now it's fine. Yeah, so this is the basic working of an LRU. I hope it was clear. Basically the whole concept is whenever you access, insert, update, you bring it to the front. And if you are deleting, then you are kind of deleting it, no need to bring it to the front. So this is kind of the easy part. Now the tricky part is, how do you maintain O of one operation for everything? So let's say you need to do a lot of frequent insertions and deletions, because that case would arise because it's a fixed size data structure. Anyways, if you need to do a lot of insertion and deletion, list is good enough. O of 1, right? But the access time in linked list is O of n, so that kind of beats the purpose. If you want good lookups or constant lookup, you can use something like a hash map. So that would make the lookup time O of 1. But how do you kind of keep a hash map sorted in a way that you get the, if you're kind of traversing over the hash map, you get the least recent or most recently used items first. So that really shouldn't happen. You can't do with the hash map unless you keep a timestamp and keep a sorted map or something. But they really, again, if you are keeping it in a sorted way, sorted map or a tree map or something like that, that would be log n time complexity, and what we want is O of 1. So what we need to do here is we need to use a mix of a linked list to provide that O of 1 in, to keep the order basically, and provide that frequent insertion deletions, and a hash map for the frequent lookup. So we will use both a linked list and a hash map combined as our LRU. Now one thing you need to understand is you need to use a doubly linked list. Why not a singly linked list? Because if you need to delete a node, you need to get access to its previous node in a singly linked list to be able to delete it, right? You cannot just delete a node directly without removing the reference to it. So what a doubly linked list allows us to do is, if you have a node, then you get its previous and you point the previous to the current node's next, and then you delete it. So you need a doubly linked list. You could try with a singly linked list, but yeah, you will not be able to get that O of 1 time complexity. If you really want, maybe you could do some kind of hash map stores the previous node or something, but yeah, I don't think that will work. And what I am about to show you is one of the more optimal ways to implement LRU. Now you could experiment, up to you. One thing to know is Java has a linked hash map. What that basically means is that you don't need to implement the LRU cache in Java. You can kind of cheat. Ideally, I would not recommend that, but see, your map is an interface, right? And it has an implementation hash map, it has tree map, it has another implementation called linked hash map, which is an LRU cache by default. So all you could do would be to just create a new linked hash map and you would be done. You don't need to do anything else. But yeah, let's not do it that way. I mean, you are free to look how it works, but yeah. So now let's just implement this question. Okay, so let us start. So this is what I'm again implementing in C++. This is what is given to us. I removed all the comments. So first thing you want is so we are storing key value, right? So we need a key value pair. Now you might be saying that, hey, hash map already stores a key value pair. Why do we need a pair? We'll come to that later, but for now let's declare a pair, and I'm using alias here so that we don't have to type pair int comma int every time. Yeah, so I'm using this alias pr is basically our pair, right? So this is where our key and value data will go, and you want to create a list, again linked list. In C++ you declare it just by this, and we will call it our cache data. Okay, so this list will actually store all the actual data. We also want a hash map for fast lookups, so we will have an unordered map of now the key will be int, but what should be the value? Now what you need to understand is, if I just show you this slide, so if you see this slide here, very good example of understanding LRU. It shows the data is actually stored somewhere else in this list, and we are using one lookup to just get to do this hash map is just for the lookup part. So basically what we want to do is all our data will go to cache data. Each node in cache data list will have the data, but from the map we want to retrieve the node which is in the linked list efficiently. So in the map, we will not store the actual value. What we will store is the node where the data is. So how can you do that? How can you store a node of the linked list? In C++, you can just use an iterator. In Java, you can just store the reference itself, and I'll attach Java code and Python code for this as well. But in C++, you can just use the iterator. So it will be a list of pair of int, and you attach the iterator type, yes, and this is our lookup. Okay, all good. Compiler isn't complaining, so all good. Yeah, so yeah, this is what we would use. This is just alias, and also we will have a int len, okay, to denote the capacity. Now in our constructor, what we will do is we'll assign length to capacity. This should be the maximum length of our linked list, or LRU data structure, as you can say. Now first let's implement the put method. So put can have three operations. If the item already exists, which is an update, if item does not exist and we have enough space, or if the item doesn't exist and we have enough space. So in the put, let's first do the part where we are doing an update. That means the value already exists. That's kind of the easiest part. So if lookup, and we are again finding by the key, right? Lookup.find key is not equal to lookup.end. That means it exists in our LRU. So what you really want to do is, what you can do two things. You can either delete the old node, create a new node with key value pair and insert it at the head, or you can just swap the old value to the head, the old node. So C++ gives you a very list has this thing called slice. Cache data has something called splice. So what that basically means is you just get the so kind of swap it. Yeah, so you want to do it at beginning, so we'll do cache data dot begin. I will just pass the iterator. Just a second. Got a call. Okay, yeah, really sorry about that, but yeah, you just pass it the iterator where you want to insert, which is begin. You pass it the data structure and you pass it the iterator. Now we don't have the iterator. What we will do is we'll get the iterator to the current key, the node which is, so we'll do something like lookup, and you pass in the key, and this will give you the iterator, right? And then you just pass it the iterator. All good. Yeah, this should be enough. And of course you also want to if you are doing a delete and inserting at the begin, then you also want to do a lookup of key equal to cache dot begin, which is the iterator to the first node. Really the implementation which I am doing via splice, you don't really have to do this, but you know, if you want, why not? Okay, so this is the part where if it, you know, does exist in the already is in our LRU and you are kind of doing an update with the value. So yeah, we didn't really change the value, right? So we need to do that. Iterator second equal to value, right? Now again you need to understand this as key value pair key node pair where node equal to key value. So you do something like this. Yep, now you can see we have a bit of repetition. We are storing key 2 times. Why? We'll have a look at it later. Yeah, so this should be good. We update the value So since we are doing an update kind of thing, we update the value, we move the iterator to the beginning, to the head, and yeah, we assign to the lookup map the new iterator. This should do. Else if, let's consider a second option. Let's consider the fact that we are already approaching the size. That means the item is already, let's just say lookup dot find key. Oh, this should be equal to lookup dot end. That means the data does not exist in our LRU yet. Now again, this check is kind of redundant, but if you want to add it, why not? And we are approaching the size, so our cache data dot size equal to len. That means we are already at our max capacity. So what we need to do, we need to delete the old data. So what we'll do here, we'll delete the old data, which we can get by if it's a list, you can just do the pop back thing, right? So first we want to get the iterator. So last iterator equal to your cache data dot back. You get the iterator, and first thing you want to do is delete from the lookup table, because again, since we are maintaining this data in two different places, the hash map and the linked list, if you are doing an insert, update or anything, you kind of want to update both the data structures. Why we didn't do it here? Because again, in the iterator itself we are maintaining the value and we updated it. So the only thing we need to maintain in our map is the key and the iterator. The value is maintained in the iterator itself, so that is fine. So we just update the key here. Again, this is not really needed because the implementation I am doing, but you might be doing a delete and insert, so there it might be needed. Yeah, so we do this cache data dot back, and we want to remove it from our lookup dot erase last iterator dot first. Yes, you delete this, and of course you again want to do pop back from our list cache data dot pop back. Yep, and this is a dangling pointer. Can we do this? I don't really know. Okay, yeah, it's an iterator, so let's leave it at that. Okay, so again, this is a dangling thing, you need to be aware of that. But yeah, so what we did, we got the iterator from the end, we deleted it from our hash map, and then we also deleted it from our list. Yeah, and then what you want to do is you want to insert the new data. Now what I'll do is I'll do it here only, because the part of inserting a new data, if the node did not, if let's say you are not approaching the capacity, that's the case 1, and you are already at max capacity, that's the case 2. In both these cases you need to do the same insert operation. So insert is something I can do outside of this if else, but delete is specific to the case where we are approaching the length. Yeah, so this delete is kind of, you can say, specific to this, that's why it's in the if else block. The common part we can just write here. So what we need to do is, first we need to do cache data dot push to the front. So again, remember, whenever we are doing an update or insert, access anything, it needs to go to the front. So we are inserting a new value, it needs to go to the front. You can make a pair, or you can just use this also, and this should work. Key value. Any issues? No issues. So now we have inserted the data in our linked list, We also want to update our hash map to reflect the same data. So hash lookup of key equal to cache data dot begin. Yeah, this is good. So now we inserted the data. Okay, let's see how it would go. Let's say if it's an update, because the item already exists, so we update the value. Okay, and then we move it to the front. We move the node to the front of the linked list, and we update the hash map key to point to the latest node, and then we return. So if we return for update, this would kind of not execute. Otherwise, if the data already exists, okay, and yeah, so here we are doing the part where the data is not already in the cache, but the cache is approaching its size. So what we will do is, first we will delete the uh, least recently used or the tail thing, and then we will insert. If it is not an update and it is not approaching the size, then this part will be executed, which is you add the data to the front and you do a lookup and just update the lookup. Yeah, so our put is done, should work. Now when we are doing get, now the condition given here is if it doesn't exist, return minus 1. So what we will do, first we will check via the lookup that if it exists or not. So we'll do if lookup dot find key equal to lookup dot end, that means it doesn't exist, you want to return -1. Okay, otherwise if it does exist, what you want to do is you want to return the value, but you don't just want to return the value, you also want to update the node to be at the front, because it was most recently used. So you need to move it from wherever it was, whether it was at the end or the beginning or somewhere in the middle, you want to move it to the beginning. Yeah, so how we'll do that, we'll first let's get access to the node itself. How we'll get that, the lookup map has that key, right? And we will do auto and old iterator equal to whatever, this will give us the iterator, right? And we want to return the value at this old iterator. Yeah, that's the issue. Oh, okay, sorry, this is the yeah, because this is a key value pair. Yeah, so the value will be at the second, so you want to return that. But before returning, you also want to ensure that we kind of swap it to the front. How you would do that, so list has this method called splice, which we used. So we'll move it to cache data dot begin, and the iterator is old iterator. Yeah, so what do we do, first thing we get the iterator, right, via the hash map, then we move it to the front, and then we delete the value. So this is what our get should look like. Looks good to me. Let's try copying this, hope it runs. Let's try running this. Yep, works. And so okay, I don't know why it's running so slowly, maybe the test cases. Yeah, so as you can see, it works. Now again, you could implement this the way I have done via splice, which is kind of a swap, or you can do deleting of the old node and inserting at the beginning. But remember, if you are doing a deletion of the old node and inserting at the beginning, then you want to update the map as well, like I have done here. Here I don't need to do it, but yeah, uh, if you are doing any operation, you want to update both of the, you can say, data structures. I don't need to here because I'm using an iterator which is a pointer, so I'm kind of internally changing it, and hash map will, since it's a pointer, it will reflect it anyway. But yeah, if you are doing it a delete and kind of insert way, then you want to update the hash map as well with the key pointing to the correct node in the list, which would be your cache data.begin. So yeah, works. That's it. Thank you. I'll attach the Java and Python code as well.